Hello! In this video, we are going to prove the following theorem. Every non-trivial finite group has an element of prime order. Now, to be a non-trivial group means that the identity element is not the only element of the group. We must be able to find some element in the group which is not the identity element. Now, let's also remind ourselves of the notion of the order of an element of a group. Given a group G with identity element E, and given A is an element of G, we say A has finite order if there exists a positive integer n such that A to the power of n is equal to E. The order of A is the smallest positive integer with this property. Now, we have proven if G is a finite group, then every element of G has finite order. Okay, so now let's get into proving this theorem. To start out the proof, let's consider a non-trivial finite group G with identity element E. And from here, we want to find an element in G that has prime order. In other words, we want to find an element G in G with the property that the order of G is equal to some prime number P. So to start, since G is non-trivial, this means we can find an element in G which is not equal to the identity element. I'll call the element A. And since G is a finite group, we know that every element of G has finite order. So in particular, A must have finite order. So let's let the order of A be equal to m. Now, the order of A is a positive integer, so we know that m is greater than or equal to 1. But the claim is that m is strictly greater than 1. Because what happens if m is instead equal to 1? Well, by definition of the order of an element, we know that a to the power of m is equal to e. So, in this case, a to the power of 1 is equal to e. But a to the power of 1 is equal to a, so this implies a is equal to e, which contradicts the fact that a is not equal to e. So we reach a contradiction. Our assumption that m is equal to 1 lends to a contradiction, so we can't have m is equal to 1. Therefore, m must be strictly greater than 1. So m is a positive integer greater than 1. But if you recall, according to the fundamental theorem of arithmetic, every positive integer greater than 1 is either prime or a product of primes. In fact, there's more to the fundamental theorem of arithmetic than that, but in any case, that tells us that m is either prime or a product of primes. So certainly, we can find a prime number p such that p is a divisor of m. And since p is a divisor of m, this means that m is equal to p times some integer. I'll call that integer k. And in fact, since m and p are positive, that tells us k must be positive. So now, what do you think is a good candidate for an element of G that has order p? The claim is that the order of the element a to the power of k is equal to p. And to show this, we want to show two things. We want to show that a to the power of k to the power of p is equal to e, and then we want to show that p is the smallest positive integer with this property. In other words, we want to show if q is any positive integer with that property, then p is less than or equal to q. So let's first show that a to the power of k to the power of p is equal to e. Now, by properties of exponentiation, we know that this is a to the power of k times p, and we know that k times p is equal to m, but since the order of a is equal to m, we know that a to the power of m is equal to e. So this shows that a to the power of k to the power of p is equal to e, which is exactly what we wanted. But now we want to show that p is the smallest positive integer with this property. And to do that, let's suppose q is another integer which has this property. The whole goal is to show that p is less than or equal to q. Now notice, by properties of exponentiation, we know that a to the power of k to the power of q is equal to a to the power of k times q. And this shows that a to the power of kq is equal to e. But since the order of a is equal to m, which is equal to kp, this tells us that kp is the smallest positive integer with the property that a to the power of kp is equal to e. Well, we know that kq is a positive integer with the property that a to the power of kq is equal to e, so kp must be less than or equal to kq, because kp is the smallest positive integer that can do this. And since k is positive, if we divide k on both sides, we get p is less than or equal to q. And that's exactly what we wanted. So, putting this all together, we have shown that a to the power of k to the power of p is equal to e, and we have just shown that p is the smallest positive integer with this property. In other words, we have shown if q is any positive integer with this property, then p is less than or equal to q. That tells us that the order of a to the power of k is equal to p. And so, we have found an element in G with prime order. So this completes the proof. And so yeah, that's pretty much it for this video.